So today we're talking about the next atomic model. We've already talked about Dalton and Thomson and then Rutherford, and today we're going to get into a guy named Niels Bohr, and his name is not as important as the Bohr atomic model. So if you look at what was known or what was thought about the atom before Bohr, Ernest Rutherford had the most recent idea about the atom, and the idea was that you had the nucleus there in the middle, the positive region in the middle, and that was very simply where all the positive charge and most of the mass of the atom was found. And then the electrons were just kind of like flying around out here, kind of just sort of anywhere around the nucleus. And that model kind of hung around for a little while. It was pretty popular, but there were some problems with it. And one of the problems comes when we look at the flame test that you guys did in class last time. So each atom gives off a characteristic color when you heat it. So for example, copper, which is Cu, gives off this pretty green flame. Potassium, which is K, gives off this light purple kind of lavender flame. And that in and of itself is kind of neat, but what does it really say about the atom? Well, when you get into it, what it says can only really be seen when you break down the light that's being given off by these elements. So just with the naked eye, all you see from this copper flame is green. But if you actually pass that light through a tiny little slit and then a prism, which we'll actually we'll do as a simple little experiment in class, what you'll see is that light can be broken down into very specific amounts of energy. So while the color that you see with your eye might be this particular color of green, you also get kind of a greenish yellow and then a yellow color given off by the copper. And you don't see as much of these last two, the greenish yellow and the yellow, just because it's not given off as much. This first one that's nice and bright green is the one that you see with the naked eye because it's the one that's given off most often by the copper atom. But the important thing we want to talk about is why is energy being given off by these atoms in only these very specific little amounts? In other words, if the Rutherford atom were the true model, and these electrons are absorbing energy as we heat them, and that energy is given back off, and the electrons give that energy back off in the form of light. Well, why is it that a copper atom can only give off a couple different amounts of energy? So why only specific amounts? You have to answer that question. And Niels Bohr figured out that electrons are absorbing energy as the atom is being heated and then giving it off in the form of light. But again, why only very specific amounts of light? Why only, therefore, very specific amounts of energy? You may have heard, you may know of the phrase Roy G. Biv. It's a nonsense word, but it stands for red, orange, yellow, green, blue, indigo, which is kind of a purplish blue, and violet. And it turns out that violet is the highest energy light and red is the lowest energy light. It's the reason that you see the sunset as red at times, because those long wavelength with low energy red light are the only ones that can make it all the way through the atmosphere to your eye at the sunset when the sun is lowest on the horizon. But why is it that only specific amounts of energy are being given off? And what Bohr figured out was that must mean that as these electrons are absorbing energy and then giving it back off, the reason they can only absorb and release specific amounts of energy is because they must be jumping and falling. In other words, as you heat up a copper atom, its electrons go further away from the nucleus very briefly to a higher energy state, and then they fall back down. But if they could fall back down to any place they wanted to, then that means a heated copper atom could give off a whole rainbow of different colors. But since it can only give off a couple of different energies of light, that must mean that electrons within the copper atom can only jump and fall very specific, certain distances within the atom. And so he came up with his atomic model that sort of followed that logic. So if you imagine this as a copper atom, and we heat up, let's say, an electron here in the second energy level, so he imagined that the electrons existed at specific distances out from the nucleus. And so like this would be distance 1, this would be distance 2, and this would be distance 3, and you could even have a 4th, 5th, 6th, 7th energy level. But let's say you had this copper atom and an electron in the second energy level or layer absorbed some heat, and that caused it to jump up to the third energy level. Well, as it falls back down, which it's bound to do because it's attracted to this positive nucleus here in the center, it's going to give off the energy that it absorbed in the first place. And if it gives off that energy, if the amount of energy that it gives off as it falls is the same as the energy of green light, then that's what your eye is going to see. It's going to see green when you look at this bunch of heated copper atoms. And so the fact that only specific energies of light are being given off is evidence that electrons don't just float and fly and zip around anywhere they want to outside of the atom. They must be restricted to these very specific certain distances out from the nucleus. So again, energy level 1, 2, 3. A good way to think of it is if you were to compare climbing a set of stairs or climbing a ladder versus climbing a ramp. Okay, so if you're on a ladder, you can only be, let's say this ladder has 5 rungs, 1, 2, 3, 4, 5 different distances off the ground. But if you're going up a ramp, okay, you can be infinite number of different distances off the ground, because just by walking a tiny amount further up the ramp, you're a tiny bit further up off the ground. So Rutherford's atomic model might have been like this, with atoms being able to give off an infinite number of different energies as their electrons are heated and excited, versus the more modern version given to us by Bohr, where the electrons have to exist at these certain distances or rungs away from the nucleus.